Hello everyone, welcome to our Big Data and AI demo session. My name is Calvin Lui. I'm a Senior Technical Product Manager at IBM Data and AI. In the next 30 minutes, let's talk about how our team of data scientists accelerate their AI at scale with IBM Cloud Platform Data, following with a live action demo. So what's the GPU and why GPU? GPU stands for Graphics Processing Units. It was designed to accelerate the rendering of 3D graphics. Over time, they became more flexible and programmable, and become one of the most important types of computing technology, which accelerates workloads in high-performance computing and artificial intelligence. We have observed a steady growth of GPU adoption since 2011, and the pace picks up dramatically in 2020 and is projected to grow by over 22% in the next 5 years. So we also observe that industry domains, they start infusing AI into their performance critical use cases, and thus introduce more advanced machine learning or deep learning algorithms which are data thirsty. And this use case and application need high computing capabilities of GPU to be able to process this large data set to train the algorithm. For example, financial industry optimize lending and liquidity while adhering to compliance mandates. Healthcare, they try to speed up image analytics at scale and improve patient outcomes. GPU is an expensive investment. For example, the latest NVIDIA A100 itself, the list price costs $30,000 USD per GPU card, and a boss, DGX boss, costs around $200,000. Our customer, they're putting down significant investment to build their GPU grid. When we talk to them, they come to us with two challenges. The first, how to utilize GPUs to get reduced total cost ownership and get better return on investment. And second, and more importantly, when they progress in the AI journey, the expanded data scientist team runs into fighting for sharing GPU resources. And that takes away data scientists' precious time on doing data science. So how do they ensure data scientists having the GPUs? By sharing the GPUs efficiently across the team of data scientists become their biggest challenge. Let's zoom in a day in life of two data scientists, Mary and Bob, fighting for GPU resources. You see in this diagram, in this picture, Mary starts her Distributor notebook with GPU kernel and start coding. And while Mary's coding, she's locking the GPU, And while that GPU sits idle, at the same time, Bob is ready for training, but he starts off GPU to train his model. The same situation turns around when Bob starts the Distributor notebook GPU kernel and lost the GPU. So in that situation, of accommodating business priority, in this case, a running job would have to be stopped forcefully, and we allocate GPU resource to higher priority job. And then you have either Mary and Bob, in this case, be an unhappy data scientist because they're going to lose the progress of their training. Now, with Watson Machine Learning Accelerator in Cloud Platform Data, life is much better. It provides the perfect response for this type of challenging situation. Our elastic GPU computing allows data scientists to dynamically share GPU-enabled servers in a multi-tenant architecture, and making data scientists very happy because they're having the GPUs at any time for data preparation, model training, and model scoring without breaking the bank. What's a machine learning accelerator in Cloud Platform Data? The architecture eliminates dedicating GPUs to a project. It reduces ID costs while improving utilization up to 33% in typical multi-tenant scenarios. And it accelerates training inference speed. And how do we do that? By elastically scaling GPU allocation to high priority workloads with close to linear scaling efficiency at very low overhead. Our solution over here helps a business rapidly bring model into production with AI lifecycle support for building, running, and managing model. So data scientists, they could take advantage of our elastic GPU computing service in multiple ways. It could be calling our REST API in their favorite IDE, such as Jupyter Notebook, or they could use our service via our UI console. Now in the next two demos, let's see how Watson Machine Learning Accelerator drives data scientists' productivity by guaranteeing to data scientists having shared access of the GPUs, and while improving the GPU utilization. And you will also see in a live action how data scientists access our service, right? Either using our UI console or by calling the REST API in the Jupyter Notebook. So before I swap over to the demo screen, so I want to spend a bit of time to talk about the scenario we try to solve, right? So we all know data scientists, they are in short supply in the marketplace. So their time, their skills are extremely valuable to the business, right, they work for. So therefore, companies, right, that we talk to, they want to make sure, right, to keep them productive. Now, we introduced this elastic distributor training. This is our key technology that will help data scientists, in this case, Mary and Bob, stop fighting for GPUs. And instead of sharing GPUs among them, you see it here at T0, right, on the right-hand side of the graph, at T0, Mary submits job 1, and right after getting all the available GPUs to scale her training. Like at T1, so second data scientist Bob submitted job number 2. So instead of being blocked and waiting for available GPUs, EDT, Elastic Distributor Training, dynamically preempt half of GPUs from job 1 and assign to start job 2. Now let's move on to a demo screen and see how that works. So first we have the first data scientist logon, right? This is copy for data login page. Provide the username and password, right? And from here, we have a project. So a project you can think of as a collection of all the artifacts, right? All the assets that you have provided this holistic view. You can see all of them available in this project space. And we'll start creating a deep learning experiment, right? Click on this experiment UI and submit the first job. So here we provide the name of the training. And we will put down the path, associate path of the data set, which the compute with the GPU, the compute pod with the GPU will get access to. And here we'll create a training definition. Right? You can use either existing training definition or create a new one. So it's up to you. It's up to data scientists when they get here. So here we'll create a brand new one. And you see here, this is a zip file, right, that contains all of the PyTorch model, the neural network model, the Python code. Right? We'll put it in a zip format and we'll go drop it off in this UI. Okay. We'll put down the naming of the training definition. And we'll select the framework that will train that neural model. In this case, we'll put PyTorch. It's a PyTorch MINS model. An execution command, such as the name of the model, and then we can also specify, right, parameters such as how many epochs I want to put in, right, to train my neural network model. I'll put 5 here. And next we select the distribution methodology, and we'll select EDT, Elastic Distributor Training here. In this environment, I have 2 GPUs, so I'm gonna select 2. Right, and create my training definition. So you see, ease of use, click fill step. I'm ready to submit my training and run and scale that and run that at Watson Machine Learning Accelerator. Okay. So right here, let's simulate this situation. So now the first data scientist log on, submit his job. We'll log out. Now we're ready. We have second data scientist coming on board, and we'll log on with a different user ID and password. Same concept, right? The data scientist had access of the same project. Come in here, right, and then start submitting, building his deep learning experiment submission. And this time we'll put this as a different name. So it's a job 2. Again, we put down the relative path of the data set. Now instead of creating a new string definition, this time we're going to reuse the existing, the first one that we create. We'll select the framework again. And then the distribution methodology, we'll select EDT. And we'll also ask for a request for 2 GPUs. Okay, now we have 2 data scientists. They both submit their deep learning model training requests in Watson Machine Learning Accelerator. Let's actually swap a wheel. Right here we will go to a different views where system admin can log in and have a holistic view to see how GPU is being utilized, right, across all the users, tenants, right, in the environment. And you see here, the first job has been submitted, and take advantage of 2 available GPUs and scale out. Now, the second data scientist coming in here is having a trouble because now he doesn't have a GPUs. So here's his option. Either he calls out the first data scientist, kill her job, right, and then they can update the model definition, the topology, so each of them can get 1 GPU and resume and start the training. However, right, that will actually kind of like blocking the first data scientist's productivity, because now her training progress will be lost. Right? Imagine, right, the first training has been submitted an hour ago, and you don't want that scene happening. So instead, you see, this taking action right away, our elastic distributed training technology, right, will recognize, hey, there's another tenant submitting a second job. So what we have to do is let's wait for the current epoch of the first training to be complete, the gradient sync across all GPUs complete, and then we gracefully preempt 1 GPU, and we assign that to the second job. And this is all action in transition without any interruption of any running jobs. At the same time, let's switch back to the carpet for data console. Data scientists, you see, this is live action, right? You can see the metric, right? The training metric is being collected, and data scientists can then monitor the progress of the training. In this case, it's a metric, either accuracy or loss, which gives the data scientist an indicator whether the training is converging or diverging. And if they don't see the accuracy, in general speaking, going up and the loss going down, that means, right, the parameters, the hyperparameters, for example, is not a good fit with the new network model training, and I'll associate with the data set. So they can terminate their training, the training run, and then retune the parameters and submit the request again. Let's say the first training complete first, right? So let's simulate that situation. So we'll stop that job, but instead let's think about this is just the first job complete. What happened is that GPU will go back gracefully to the available resource pool, and you see the low latency and the quick response of our optimized scheduler. Recognize, hey, there's GPU sitting idle in the resource pool. How about we pull that GPU and auto scale out the second running jobs, and then expedite the training progress. So let's move on to the next demo. Same use case, same situation, same business challenge. We have 2 data scientists, right? They're competing for GPUs, and let's see how now they can access our elastic GPU computing service through a Distributor notebook. And you see here this different view, right? So we have a Distributor notebook service built in Watson Machine Learning Accelerator. And you see here each of the user, right, and Min and Calvin, right, they have start their notebook and the corresponding kernel. And the other thing I want to show you quickly is going back to this resource utilization view, and the CPU, right, will start with the Jupyter kernel, but at the same time, right, we are not actually locking any GPUs, right, at that point, because there's no request of training a neural network model yet, right? So this is different from open source, right? In open source technology, when you start a Jupyter notebook with GPU kernel, you actually lock up a GPU, so it's sitting idle until you actually send the job, right? Send the training request and train your neural network with that corresponding GPU. Okay, so we'll start with the first notebook, Calvin, right? And here, this is out of box sample notebook, right? So when you install our Surface, you will have this notebook preload in your environment. And you see here, let's get started and train that PyTorch model using Elastic Distributor Training EDT. So we start with defining the environment variables, right? So the location where you can save the log, right? Save the model, get the data set, etc. And then we define a very straightforward, right, simple PyTorch model, and along with the optimizer and the parameters like the learning rate. Next, we will define and download using the PyTorch data loader function, and we will download the MINS data set. And that's the last, right? Last, we would define the number of epoch, the batch size, and then the GPU we want to leverage to scale out that PyTorch training. And we will then instantiate the Elastic Distributor Training EDT library, right, instance, and then we'll invoke the API, right? And by invoking the API, we'll pass on the epoch, the GPUs, right, and the batch size we want to train that neural network model. So we kick it off, right? And you see here, instantaneously, right, the PyTorch model will take 2 GPUs, right, and then we'll scale and start training. So you see the difference here, right? We're not taking the GPUs. We're not locking that GPU until we actually invoke the EDT API and then kick off the training. Then we'll take the 2 GPUs and start running. Now, let's move on and jump to second data scientist, right? So the user, in this case, admin. And over here, again, we will load the TensorFlow notebook, and we'll see how we can submit that training of TensorFlow model and then share the GPUs from the first job. So again, we define the environment variables. I'll go through quickly here. And then next, we will define this TensorFlow model, and again, the data loader where to get the MinCNN data set. Okay. Next, it's the same code, right? We would define the batch size, number of epoch, and then the number of GPUs we want to scale out that TensorFlow model training. Again, we instantiate the EDT model instance, and we pass on the neural network model, the dataset function, along with the loss function and optimizer. And at last, we invoke the EDT API, right, the .train method, and we pass on all these parameters. Okay. And you see here, right, I swap back to number 1, the training, and you see we pull back, right, instantaneously the training metric, right, the accuracy and loss, right, and this is refreshing every 10 seconds, right, along with the number of iteration, right, that we are, so the data scientists they can monitor their the GPU train progress in the notebook interactively. So going back to this view, right, holistic view in terms of GPU utilization across either line of business or different tenants in this grid, and you see here quite robust, right? And right away when the second job was submitted in the Jupyter notebook, the scheduler recognized, hey, now you have 2 tenants, so we need to share the GPUs across these 2 tenants. And when the first training finished the first epoch, it would then preempt 1 GPU, and then we allocate on the fly to the second training, right? Second training running invoke in the second Jupyter notebook, and you see the effect, right? There's twofold, right? One is this dynamic scaling of GPUs ensures higher productivity of both data scientists in this case, right? And how do we do that? We guaranteeing ensuring that two data scientists, when they need a GPU, they will get a share of it. They will get a share access of the GPU for doing either the data preparation, the data training, or even model scoring. And secondly, it drives GPU utilization. So when their GPUs sitting idle, right, and not being used by any other tenant or any running application, any job, we can do auto scaling. Now let's move on to the next demo and see how Watson Machine Learning Accelerator automate model search, model parameter search, can help business to accelerate time to accuracy and drive time to business insight. So what is hyperparameter? It's such a value to control the learning process of neural network. For example, you can think of typical hyperparameters includes the model architecture, the optimizer, running rate, etc. So the value, right, can have an important effect on training result. A model trained with wrong hyperparameters may not converge or converge to suboptimum parameters. So typical out-of-box open source solution runs sequential on a single node, single GPU. And now the number of combination grows very quickly, which means it's intractable, right, for data scientists to test single parameters one by one. What we help here is with our auto model hyperparameter search, we enable tens of parallel jobs with 10,000s of iteration, while we're handling the resource allocation and monitoring of all results. So while searching the optimal model parameter value set, and you can select your favorite search algorithm. Out of box, we bundle random TPE, Bayesian, Hyperband, and research. And data scientists could also bring in their own innovative search algorithm and running that in Watson Machine Learning Accelerator. Now let's move over to a live demo and see how that works. So this is Jupyter Notebook. Again, we are leveraging the REST API to access the automate hyperparameter search capability. So first of all, we will define the environment variables to lock onto the REST API server. And next, we'll connect to the REST API server and try to retrieve the list of either its existing hyperparameter experiment or where there's any running hyperparameter experiment ongoing in the cluster. And next here, where we define coupled parameters. For example, what is the algorithm, right, you want to leverage to do the search of your parameters. So in this case, we put random, right, for this simplicity of this demo. And then there's a control plane where you can define how long you want to automate your parameter experiment. Either is by the upper limit of the time, in this in minutes, right, 60 minutes, or it defines by the number of experiment you would like to run and execute. So in this case, put maximum two jobs, and then here is where you define how many experiment you want to run in parallel, right? And this case, this grid has 2 GPUs, so I put 2 here, and then you define your metric, how you want to measure experiment output. So we leverage the minimize strategy, and with by measuring the loss value per experiment. And then last, we can define here what parameters we would like to search. We put down learning rate, which is searching in a range from 0.001 and 0.1. You can define as many as hyperparameters you would like to search in each of the independent experiment. So let me run it. So it gets started, right? So we comes back with the experiment ID. And then again, we can leverage the same REST API. And you see here, it starts pulling the status of each experiment, and we have two here, as we defined in the input parameters, and it will run for a couple minutes. So we'll come back to this in a few minutes, and we can see the result of the auto hyperparameter experiment. Now you see here that 2 of HPO experiment complete. Now imagine one of a customer, for example, they're running thousands of experiments across their 64 GPUs overnight. Passing through each experiment result to try to get the optimum hyperparameters would be painful. So instead, our REST API, right, with the algorithm, we search which experiment would generate the optimum value set of hyperparameters, and we can display and pull that at the top of the REST API JSON object result. And you see here, the first job, returns the best value and best outcome of hyperparameters. And you can also you step through, right? You can also we pull all of each experiment. What is the input learning rate that we select by the random algorithm? What is the coming back metric, right? The loss value, and etc. I would like to wrap up our presentation with one last topic. StepML is a Python library for high-performance machine learning training. It offers state-of-the-art CPU performance and with additional support for GPU acceleration. StepML supports some of today's most popular machine learning models, including linear regression, logistic regression, SVM, random forest, decision tree, etc. And in this diagram, you can see a field comparison of runtime between training machine learning models in scikit-learn and with StepML, both in CPU and GPU. And acceleration of up to 100 times can be obtained depending on model and dataset. At the same time, this acceleration is almost seamless to the user. For data scientists using Python, only minimum code change are needed to the existing code to take advantage of StepML. Here's the sample of using logistic regression model in both scikit-learn and StepML. And by simply importing the StepML library, right? Another example of XGBoost model in both scikit-learn as well as using the StepML. Any of this demo, right, live demo that I showed you today, you could actually find those sample notebook models in our guided learning path. At the same time, I encourage you to visit our website, our show and tell videos, right? Lots of resources that you can explore to get further insight of what's a machine learning accelerator. I also put up my email, right? So if you have any further follow-up or inquiries of what's a machine learning accelerator, please feel free to drop me an email, and we will continue and start a conversation from there. Thank you for your time watching today's webinar, Accelerate AI at Scale with an integrated data and AI platform. Have a good day.